as you can see, we're deriving the cubic, quartic, and the quintic formula possibly today. And let's see how much we get through. So let's start. Deriving the quadratic formula. So everyone should be able to do this, right? What you do is you have a quadratic equation and you complete the square, right? And then when you complete the square, you get this result, which is the quadratic formula. That's pretty straightforward. I'm going to assume everyone is able to do this. All right. But actually, there's another way we could do this, and it's called by substitution. And what we want is, the aim of this substitution is to make it into the form x squared equals a. So when we have this form, when a is a constant, we can solve this easily because we just plus or minus square root of a. Yeah? So let's see what we could do. Let's try this substitution, right? X equals y plus k, where k is an arbitrary constant. When we plug it into our ax squared plus bx plus c, we expand everything out. And we get this term, right? We have the 2ak y and the by term over here. And we want to remove the y, the linear term, because we want to make it only the quadratic term. So then we can make it really easy. So what we could do, because k is the arbitrary constant, we equal this to 0 by comparing both sides of the coefficient. And we see that if k is negative b over 2a, then the linear term will be 0, right? Can I do this now? So let's do that now. Let's say that x equals y minus b over 2a, and sub it right in. Let's see what happens. So we see that after some expansion, we can see that the negative by and the by cancels out. That's what we want. And we are left with ay squared plus b squared over 4a minus b squared over 2a plus c equals 0. And if we rearrange everything to the other side and we'll put y on one side, and when we square root of that, we can see that that's very similar to the other side of our quadratic equation. And then we just realize that x equals y minus b over 2a, right? So substituting back in, we have our quadratic formula. Negative b plus or minus b squared minus 4ac root over 2a. Yeah, that's pretty straightforward. Yeah, and the substitution here is just shifting the turning point to the y-axis. And that's interesting, but we're going to move on to what we want to do today. It's a cubic formula. So we're going to use a similar approach where we substitute something to make it into like x cubed over equals a. So that's really easy to solve. We just cube root both sides, right? But we can't do a substitution, but we want to substitute twice, right? Because we substitute once to eliminate one term, and then substitute twice and eliminate two terms. So what can we substitute to do this? So we turn this into what we call a depressed cubic by removing the x squared term. And this substitution is like our substitution we just did, which is just going to be what x equals y plus k. It's the same substitution. And once you substitute that, let's do some expansion. And we see that the y squared term consists of 3ak plus b, right? So we say k equals negative 3a over b, we have what we want. Oh, negative b over 3a. So we substitute that back in and do some ouch, and we get to this point where we see that the negative by squared and by squared terms cancel out, and we're left with some depressed cubic with y cubed, y, and the constant term. And we could write this like that, right? So it's very clearly a depressed cubic. That's what we call depressed cubic. All right. And this transformation just shifts the graph similarly to the y-axis, but this time it's a point of inflection of the cubic instead of turning point. All right, so now we have our depressed cubic in this form. What can we do to it, right? Well, you might be able to want like y equals like u plus k would work, but unfortunately that doesn't work. So what we need to do is we assume that it's a sum of two variables, and uv could be anything. It just has to be two variables. And let's just sub it in and see what happens, right? So we get this, we expand that out, and we get this, where we have u cubed plus v cubed plus u plus v times 3uv plus p plus q is 0. And this part is the hardest part. This is what Cardano did, and he realized that we could eliminate this term if we have this equal to that. Or this is 0, then this removes that, and that'll be easy to solve, right? Because this is, it's easier. It's going to be easier to solve in some way, and because we have two variables, we could set a constraint on one of them, and how the other one will. So if we have a constraint of one of them, the other one will be affected by the same constraint, and that'll be fine because we're using two variables to solve for one. We're not going to lose any possible values by making one of them constrained. So,
I have a question, sir.
Yeah.
So with the roots of the equation, they can be complex.
Right? Yeah, they can be.
Squared v, but wouldn't that give you a different answer if you have like I squared? They give you a negative.
Do we square v? Do you mean here?
Yeah. Like,
that's just an expansion. Like
it'd be different if it was complex.
Yeah, but we are assuming the values to be they could be complex, but there's nothing stopping them from being complex from the first place. We did not say they're complex or not.
Different plus or minuses.
Well, everything here is it's all algebraic. So this doesn't matter what this number is. It could be integer, it could be a complex, it could be real. This is always true, right? U plus v to the cube. It's just u cube plus 3u squared v plus 3u v squared plus v cubed. That's always true, no matter what number system you're using. So we don't have to worry about whether or not it's being complex. But that's interesting thought. We'll come back to where are the complex roots after we do this, if we have time. So what he did is to do that, and we substitute in like y equals, we have this equation where we want this to be 0, so we remove this term. That's what he wants to do. And let's see what that leads to, right? So if we put that back in, we remove the u plus v term from here. Yeah, if we remove this term, we're left with u cubed plus v cubed equals to negative q, right? And we have this. Because we know what uv is, we could have u cubed v cubed is u cubed times negative p over 3u cubed, because we want negative 3 uv to be p, right? That's what we want. And we see that u cubed v cubed is negative p cubed over 27, and u cubed plus v cubed is negative q. So what does that look like then? Does anyone recognize this? Yeah.
This is just two symmetries equation of two variables where you have x plus y equals something, x times y equals something. And it can potentially like form a quadratic equation out of this by squaring the first one, so you can solve both x and y pretty easily.
You mentioned quadratic expression. What if I name this alpha? What if I name this beta? What does that look like? Roots of polynomials, right? You see that that's where this substitution, it's the critical point. We could express this as two systems of equations which satisfy what a quadratic is, because those are the two roots, right? And now we can see that, yeah, those two systems are just the sum and the product of u cubed and v cubed, right? And this is a definition of the quadratic roots. So we're going to use roots of polynomials here. If we let the two roots be u cubed and v cubed, we know that the product is the c term and the sum is the negative b term. So we can rewrite this as this quadratic equation. And we could solve this quadratic equation because we have our quadratic formula, right? So if we solve this using the quadratic formula, we'll get the two roots to be negative q over 2 plus or minus root q squared over 4 plus p cubed over 27. That's from a quadratic formula. And this means that our two roots, which are u cubed and v cubed, would be those two roots, right? That's what we name our roots. So we could cube root those roots to get what u and v are, right? So we cube root both sides. This is our u, this is our v. And we remember that we define u and v to add to y. So we're going to write y equals that plus that. Does this make sense? We're following, right? All right. So now we can do our general cubic formula now, because we just sub this back into, we have this equals p, this equals q from what we did when we depressed it. And we could substitute that back into the depressed cubic formula, which we just derived. And this is what we have, right? And we could simplify things a bit over here. And we're missing something though, because this is in terms of y. So we need to put in, recall that we have x equals y minus b over 3a. So we put that back in. This is our full general cubic formula. And at this point, we could do an example, but I don't think it's necessary. So just trust me, this is the right formula. And I'll type this in, the whole thing. It's just a bit of copy and paste, but yeah. All right. But as we mentioned, there's complex roots, right? The equation over here only gives us, oh, that's pretty cool. The equation over here only gives us one root, right? Because this gives you one value. There should be two other equations that gives you the other two values, right? So where are they? Now we're going to talk about, let me see, yeah. We expect 3 from a cubic equation. So like in the quadratic case, there is plus or minus that give us two roots. But there's no plus or minus over here. So the two roots are found actually if we multiply u and v by the cubic roots of unity. Not unity. Oh. And I'm going to talk about what the cubic roots of unity are right now. So this is a bonus. I think we have the time. So roots of unity. What happens is, if we want to visualize the roots of where the roots of unity comes from, we need to look at the complex plane. So if we consider the equation z to the n equals 1, where z is a complex number, you can express z as e to the I using Euler's formula. So I have this. And we see that the roots of unity will be cos 2 pi k over n plus I sine 2 pi k over n, where n is a natural number and k is also a natural number. Oh no, n is the number here and k is any natural number. Or it could be integer actually. And then you see that the cubes of, if we use this formula, the roots of unity are 1, a half plus I root 3 over 2, and a half minus I root 3 over 2. And to visualize this geometrically, put them in the Argand diagram, we see that it forms an equilateral triangle. And that's the property of any generic roots of unity, is that they are going to form a regular polyhedron with sides n. I'm not going to go into why, but it's pretty interesting if you want to know more about it. Maybe I'll cover something more in the future. But back to what we have. Right, we want to find the other two roots. So firstly, we have this. We have the first root, which is u plus v. The second root is the cubic of unity times u plus cubic of unity squared times v. And the cubic of unity squared is just the other side, because that's the property of cubic roots of unity, where cubic of unity to the power of n plus 1 is just the next cubic root of unity. So you could write this as omega squared, actually. And the next one will be omega squared u plus omega v. So why is this the case? So because these two variables have to multiply to negative q, right? So we can't do omega u plus omega v because that does not multiply to negative q. And the property of the cube roots of unity is that cube is a solution to 1. So if we multiply these two terms together, we get omega cube times uv, and omega cube is just 1. So that satisfies that. And this as well. So we can't do any other possible combinations because these two are the only ones that satisfy this constraint we had at when we do Cardano substitution. So we put in a full cubic formula. We get these three roots. So this is the first one that we're familiar with. This is u, this is omega, this is omega squared, this is v. And you can see, yeah, this is just the other way. So yeah, this is our cube root of unity. And there's an interesting thing here. We could look at the cubic discriminant if we want. And what is the cubic discriminant? Remember in the quadratic, we have b squared minus 4ac is the quadratic discriminant, right? And that actually is from our square root. Because the square root can give imaginary, could give repeated roots, or it could give two real roots, right? A square root. And we have the same square root over here. So we're going to name this part our cubic discriminant. So let's see. And I'm going to use the dispersed cubic because that doesn't make any difference. It's just change of variable. And this discriminant is described as this, which if you remember, that's what's inside our square root, because that's the same definition of what the discriminant is from the quadratic. So the cases are very similar to what we have in a quadratic. So if it's greater than 0, there's one real root and two complex conjugate pairs. What that means is there's only one x-intercept in the whole graph. And then when it's equal to 0, there's 3 real roots and at least one duplicate root. So what it looks like is there's going to be a repeated root, and then there's also one more root, which is elsewhere in the graph. And then the last option is 3 real and distinct roots, where all 3 of them cross through the x-axis. And that's how we define the discriminant. That's pretty interesting. So you can know from discriminant whether or not how many solutions we expect that are real. Should we move on to the quartic then? Yeah, I think we have time. So the quartic formula. The first question to ask is, can we do the same? Like, can we derive this? And let's try, right? It should be very similar. We should be aiming for x to the 4 equals some constant. That's what we've always been aiming for. So we can first depress it into this form. Then we remove the y term. So we do the same process. We substitute y plus a constant. But I'm not going to do that process because it's the same thing. Interestingly, it's b over 4a this time. So the first time we did b over 2a, second time b over 3a, b over 4a is a quartic. So maybe you guess a quintic would be b over 5a, right? A hexatic could be b over 7a. But let's see. We're going to focus on our quartic now. So we do a lot of ouch actually. And then we see that it can be reduced to a depressed quartic because the b cubed terms here cancel. If I point out where this is here. Where is it? Here. This one is here and this one's here. Yeah. So the b terms cancel out. That's what we want, and that's our depressed quartic. That's the easy part, right? Now we have to do another substitution, which is unusual to what we usually had, right? So remember in the cubic formula we did a cardinal substitution. We have to do something similar because we can't use a normal substitution. That doesn't work. What we're going to do is use Ferrari's method this time, and this is the guy who discovered this. And there's actually more than a way to do this process. So like cardinal substitution is not the only way to solve a cubic formula. There's other substitutions you could use, and there's other methods, which some of the methods include like hyperbolic triggers, so I don't know why, but that's interesting if you want to know more. So let's look at our substitution. We could rearrange this into this equation, right? This makes sense. If we add ay squared plus a squared on both sides, we complete the square on this side, and this is some constant. Or it's not some constant, it's something else. So complete the square. And we want to make this also a square, so we could root both sides, right? That's what we want. But how can we make this a square? That's going to be a problem. And what Ferrari did is we're going to introduce another helper variable like we did in the cubic. We only need one this time. And we're going to consider this squared. So we see that this part matches this part, and we have extra terms over here. Yeah, the m terms. And that's going to help us in some way. So we could replace y to the 4 plus ay squared with this, because we have this, right, in here. So we see that we're going to remove one of the ay's, and we're going to remove y to the 4. So we're left with this. Right, we remove one of the ay's and we remove y to the 4. It becomes this. So it becomes, we reduce it to a quadratic. That's the important part. We have a quartic here, right? We have a quartic here. That's going to be really hard to deal with. We reduce this into something perfect square and something with a quartic. And we could make a perfect square, right? What can we do? Complete the square to make a perfect square. So let's complete the square, right? And we're going to get this. So firstly, to complete a square, we want the discriminant to be 0. That's what it means to be completing the square. Or we want it to be a perfect square, so that discriminant has to be 0. So, what is the discriminant? B squared minus 4ac. That's just discriminant in the quadratic. So we could rearrange and do some algebra, and we are left with a cubic. And now we could use the cubic formula that we have, right? That's the whole point. We've derived the cubic formula. It's leading up to this point. Maybe we need to derive the quintic one. We might have to use the quartic formula. But let's look at this. So we can find m such that this has a discriminant 0. I'm going to do this later because I don't want to do a bunch of algebra. But we can see here, once we have this, we see that we can root both sides because this is what we have when we complete the square. And we know that this is always going to be a perfect square because discriminant is 0. So we have the two roots to be this when we have this. Yeah? So now we're going to do all the algebra right here. So this gives us two equations in y. Yeah? And the first one is this, the second one is this because it's plus or minus. We move everything to one side. Then we could use the quadratic formula once again to find what this is. So y1, y2, y3, y4 is this. Then, substituting back in x equals y minus b over 4a, we get our 4 roots like this. And this one looks pretty nice compared to the cubic one, right? But remember, this is the depressed one. We have to put in what a, b, and c are, and what m is, right? We want to find m. So let's first look at, yeah, we want to put that back in, right? So we solve the discriminant. The first thing we want to do is solve m. So we put that into our cubic formula, right? Or we want to find any roots could work. I don't know why any roots work, but it's true that any roots work. You can use any of the 3 roots we have. So I'm going to use the easiest one with no cubic stuff, right? And we're going to substitute that back in to here with m. So we're going to replace every m here with what we have here. And that's going to lead us to the full quadratic formula and quartic. And this took me so long to type it in. But let's look at this. Can I zoom in? Yes. Oh, I don't think I can zoom in anymore. Okay. So I can explain a bit. So we can see it's quite repeating, right? This looks like that. Like the whole thing looks like 4 pieces of puzzles. So if we notice that this is our a plus 2m term, actually. This is our m term. This is our a term. And then this is another one. So if we compare what we have before, yeah, that. So you can see a plus 2m happens to be everywhere. And that's true for the full quadratic formula, a quartic one. So you can look at it, but I don't think you can see much. And this works for any a, b, c, d. We are real coefficients, all complex, I'm pretty sure. And there's one more thing, because we have time. Yeah, we have time. Let's look at the quartic discriminant. It's the same thing as the cubic one. It's just we look at the depressed cubic and we look at what's inside the square root, and we find out it's this. And it's the same process, right? We look at what happens when it's equal to 0, when it's greater than 0, and what's less than 0. So if it's equal to 0, there's at least 2 repeated roots. So there's going to be either like that. I actually have a decimal graph, but I don't think we have the time for that. And greater than 0, it will be all real, or 2 pairs of complex conjugates. So this means that there's either going to be 4 real solutions or 0 real solutions. Yeah. And then when it's less than 0, there's one pair of complex conjugate and 2 real distinct roots. Now, quintic formula. Can we do this?
No, it doesn't exist.
Well, it seems to exist, right? We could do what we did before, like we do substitution, we could do a lot of stuff. But actually, it's proven impossible to derive a general one, but we could do a specific one. There is several conditions that needs to be met, but there do exist quartic formula, but not just a general one. We could do it in different cases, but we're going to do this next time. And here's a sneak peek.
What do you mean by like cases? Does that mean like a certain variables equal something?
No. there is something called some conditions that the polynomial has to satisfy in order for what we call use elementary functions to define our formula. So we can only use plus or minus, multiplication, division, and square roots, cube roots, any nth roots. And that has some restrictions on what kind of roots we can have. That's my sneak peek for next time. But thank you everyone for being here.